The exam will focus on chapter 6, 7, a little bit of 8 because we didn't really do much there, and 9. But no 5. We skipped chapter 5, so we'll come back to chapter 5 later in the semester. It is a cumulative exam, so it will have things from the first 4 chapters, but mostly just as it applies to the other things. Like, you have to be able to do conversions, you have to be able to know the ions to make the compounds, that kind of stuff. So that other stuff is in there, but I'm not going to pick out some random fact from chapter 2 and ask you about it. So if you can do, and I will post more practice from chapter 9, kind of like what I did for the equation stuff, so you can work on that if you want. And if you can do the homework primarily for chapters 6, 7, and 9, that should be a good indication of what's happening, what will be on the exam. We'll also have time in class on Tuesday when we come back. If you have any last questions, review kind of things, and you can email me throughout the break. That is fine. I'll get back to you. All right. So we talked about solutions, and then we did this lab yesterday, which is great because I can refer back to the lab, and we're going to look at some of the data from lab and how that applies to all this stuff today. But we talked about making these solutions and how you have these different kinds of polar versus nonpolar solutions, which we saw in lab yesterday. So the things like cyclohexane is like this with carbon and hydrogen stuck together through dispersion forces, which means ionic compounds and polar compounds like sucrose or water would not mix with it because they would stick with their own types of forces. And then the opposite with the water and those things. So take a look at those and make sure that you can identify whether or not something is polar based on its experimental behavior. So if I said an unknown substance, when placed in water, forms 2 distinct layers. Is that unknown substance polar or nonpolar? You would guess it's nonpolar because it doesn't mix with the water. You might not be, I mean, that might not be true depending on the unknown substance, but the correct answer to that question is, I think it would be nonpolar. Similarly, you should be able to look at a structure and say, oh, okay, this thing has a lot of OH type bonds. That's probably polar. Or this thing is only made of carbon and hydrogen. That's probably nonpolar. So same thing like what we did in a previous chapter where we looked at what types of forces are present, intermolecular forces, hydrogen bonding, all of that. We'll also apply that to solubility. All right, so take a look at that in your studying. Today, we're going to look at some more of the calculations involved with concentration, which will be pretty much our last calculations for this semester, I think. So it'll be one more way of figuring out how much stuff is in something. Before we do that, well, one of the things we need to look at then, which is what we did in lab yesterday, is what we call solubility. Now, I know the last thing we put up with there was also solubility. That was in terms of polarity, but how do we actually measure solubility? Remember in lab, when I did those demonstrations, I mentioned that this is not really a quantitative measurement. We're just kind of shaking it and looking at it. I'm pouring kind of randomly. If we really want to know, is this more soluble or is this more soluble, then we need to do a measurement and do it carefully and calculate it. And the way we do that calculation usually is to calculate the solubility as grams of solute per 100 grams of water or whatever you're trying to dissolve something with. 100 grams of salt. We're going to talk about it only in the context of water here. That tells us, if we think about what that means, that tells us how much solute can dissolve in 100 grams of water, in a fixed amount of water. So solubility can be defined as how much solute can dissolve in 100 grams of solvent, in this case water. So we have this chart from the book called the solubility chart, which is also what you will be making in the lab write-up that's due in a few weeks. So you will see a curve like this where the solubility, that grams of solute per 100 grams of water, is graphed versus temperature. And different solutes are going to have different behavior in that range. So some are very linear. You see something like sodium chloride, its solubility doesn't change a whole lot over temperature. It goes up a little bit, which means you can get a little bit more in hotter water, but not a whole lot. Potassium nitrate, this orange curve, which is what we used yesterday, you can see there's a big change, which you noticed yesterday. You heat it up, suddenly all the stuff that is just sitting there can just dissolve right away. And then depending on how much you had, it would come out at different temperatures. There are also solutes not shown in this graph that have the opposite behavior, where the solubility goes down with increasing temperature, but that's unusual. Most substances, most ionic substances like this, as well as glucose, solubility goes up. You see this glucose curve is even steeper. Right? As you warm up water, you can really dissolve a whole lot of glucose. And I mean, you've probably seen that, like if you try to dissolve sugar in your, glucose is not sugar, that's sucrose, but if you try to dissolve sugar in like something cold versus something hot, it's a big difference. You put a packet of sugar in your iced tea, it all just goes to the bottom. But you put a pack of sugar in your coffee or hot tea, and it dissolves right away. So that's this is an indication of that happening. Let's take a look then at our data from yesterday and actually see how it fits on a curve like this. So we're going to be looking at, this is linked on Blackboard, by the way. This is everybody's data, and I don't know how good it is, but we're going to check it. So we want to know the amount of potassium nitrate, which is the mass. So that's going to be this column here, the mass in grams. And the y-axis is the solubility. So the solubility is the concentration. Because at that particular temperature, or I'm sorry, we're not going to use the mass. We use the mass to find the solubility. We're going to graph that versus the temperature. So the concentration of potassium nitrate is the concentration that you made by putting a certain amount in a certain amount. And then the temperature is when it crystallized. So when was it exactly saturated with that much solubility? So this first example, I don't know whose these are. I'm not going to put the names up here. But at about 46 degrees, we got about 83 grams in 100 grams of water. So we can look at this graph. What did I say? 46 or 47 and 83. So that's like in the middle here, 47 and 83 is about there. So that's pretty good. That looks like pretty much on that curve, right? The next group, or the next person, got 64 at about 36 degrees. So 36 degrees is like maybe here. 64. So that one doesn't look so good, right? Right, so that one's not quite on this curve, assuming this curve is correct. Whoever this is, this person, well, let's think about what that error was. So if they overestimated the solubility, that means that the temperature probably should have been higher. So that means that this person might have waited too long to, assuming the calculations are correct, this person might have waited too long to say that much had to say that it had crystallized. Remember when it was cooling down? If you wait a few extra degrees, that would throw you off the line, because really we want to be, if that is indeed the correct amount, we want to be over here. So that probably means that some crystals started coming out just above 40 degrees, but this person maybe didn't see those, and so waited until more of them were coming out, and that temperature was a little bit too low. Again, I'm not going to look at the names. I don't care who did it. All right, so this next one then, 133 and about 70. 133.70 is right in the middle here, and 133 would be about here. Right? So that one's a little bit in the air the other direction, a little bit off the curve this way, meaning that's not as far from the curve, but maybe this one is they called it a little early on maybe the temperature, the thermometer hadn't caught up yet to what the actual temperature was, because that happens at the higher temperatures. So anyway, I'm just guessing here, but obviously experimental data is not going to be perfect. This one was 62 and 38, so 62. 38 degrees is here, and 62 is here. So that was about the same concentration, but closer to the line is that other one, and so on. So you see that what I'm doing here, this is what you're going to do in that chart in the lab. And the idea is, once we graph everybody's, the errors kind of balance each other out, and we get a pretty decent curve that approximates the true curve. That's why we use everyone's data. If you alone, if each person alone did multiple trials, you would expect that you would be the same amount wrong for each one. So we're better off having everybody do it in different way, differently, and then averaging them together and see. So anyway, that's our solubility. This also brings us to a couple terms that we should know. Saturated and unsaturated solutions. So what's a saturated solution? Right. Right. Saturated means we're out of room here. Try to write small. No more solute can be dissolved, and unsaturated is the opposite. More can still be dissolved. So at that temperature, the solubility tells you the concentration of a saturated solution. So at that particular temperature, let's say at whatever that temperature, well, let's look back at our table because I don't know what those numbers are. So at 47 degrees, 46.5 degrees, a saturated solution is 83 grams per 100 grams of water. That's the most you can get in there. And what would happen if you added more solute than that at that temperature? What would happen to it? If you have a saturated solution and you add more solute, what happens? Yeah, but let's say you keep the same temperature. Nothing, right? The solute would just fall to the bottom of the container. So that's often how you can tell if you have a saturated solution or not. There's a picture in the book that shows that. Right, so here's an example of an unsaturated solution and a saturated solution. A saturated solution will always have some amount of solid on the bottom as it's going back and forth from solution. And I don't know if you noticed this, but the sodium chloride solution that we used for part C of the lab yesterday was a saturated solution. And it had sodium chloride kind of stuck floating on the bottom of not floating, but sitting on the bottom of that container because it's a saturated solution. So if you ever wonder when we're using stuff in lab, like, oh, why is this stuff stuck on the bottom? Should I shake it up or something? The answer is probably no, you shouldn't. That's a saturated solution that's supposed to be there to make sure that the solution stays saturated. All right, so that's some definitions of solubility. And so then back to that lab yesterday when we looked at the demonstrations of like the polar versus nonpolar. If we wanted to be really quantitative about that, we would measure how much stuff is dissolving in that solvent versus in the other solvent. And we would say, oh, okay, this one had 2 grams per 100 grams of water, and this one had 50 grams per 100 grams of water, so that one's more soluble. Because even things that are nonpolar can sometimes be very, very, very slightly soluble if you have careful enough measurement techniques. So we would do something like that. All right, so to measure those things, we need some tools, some numerical tools to actually say how much of something is in something else when we're dealing with solutions. And that number that we use is called a concentration. And a concentration is a measure of solute per unit of solution, or sometimes per unit of solvent. These measures that we use are going to all be solution, but I'll mark it here. Some concentration measures are per amount of solvent rather than solution. So how much solute is in a certain amount of solution? This is very important for whenever you need to use a solution, because when you measure the solution, you mostly care about how much of the solute is getting into whatever you're doing. But how much could change depending on how much was in the solution in the first place. We can't just weigh out the solution like we can a powder. So we need to know how much solute was in there, and we use this idea of concentration to do that. So we're going to talk about 2 measures of concentration. There are lots more. The book has more, but I don't want to confuse everybody, and there's only 2 that are listed on that course, the objectives for the chapter, so we're just going to focus on those 2. And those 2 are percent by mass and molarity. So let's look at percent by mass first. It's a little easier. And one of the most frustrating things about solutions is that there are many different measures of concentration. There's percent by mass, percent by volume, percent mass by volume, molarity, molality, normality, equivalence, all kinds of stuff. And those are just ones I'm listing that you'll probably see in the healthcare field. The healthcare field is notorious for non-standardized units. So this thing is measured in molarity, but this thing is measured in percent by mass, but this thing is measured in equivalence. And you know, whatever they started measuring it in 100 years ago, that's what it's still measured in a lot of cases. I don't know if you've noticed that with things like medications, where sometimes it's milligrams, but sometimes it's units, but sometimes it's, I don't know, something else, grains or something, but that happens. So we have to have a sense of what these different units mean and how we can switch between them. Well, percent by mass is kind of what it sounds like, percent by mass. What percentage of a mass is the solute? Mathematically, the equation looks like this. It's going to be the mass of solute divided by the mass of the solution times 100%. This is a really useful concentration from a solution making standpoint. This is the easiest one to use if you have to make a solution. If somebody says, I want a whatever percent solution, it's pretty easy to do. So let me show you how that works. Let's say we want to make a solution with .30 grams of sodium chloride in 120 grams of water. So we take 30 grams of sodium chloride, 120 grams of water. We mix them together, the sodium chloride dissolves. The concentration of that solution is the mass of the solute divided by the mass of the solution. So that looks like this. The mass of the solute is the 30 grams of NaCl. And the mass of the solution is everything together. So that 30 grams plus 120 grams of water. So 30 divided by 150 is 0.2. And then we multiply that by 100%. And so that's going to be 20% by mass. And the symbol for by mass is mass over mass. That's so everybody knows what units you're talking about. There's also V over V and M over V. So it's important to know that this is by mass. The tricky part here is that, not really tricky, but the thing to remember is the denominator, the bottom of the fraction, is the total mass of the solution, not the mass of the solvent itself. That's different from solubility. Solubility was per solvent. Concentration percent by mass is per solution. So how would you actually do this? Well, let's say, let's look at it the other way. We're going to use the same numbers, but what's probably more relevant in a lab situation. You might say, I want a 20% by mass sodium chloride solution. Well, let's do it this way. I want, let me add something else here. I want 100 milliliters of a 20% by mass solution. Excuse me. Actually, you know what? That doesn't work. We can't do that. We'll do that the next way. That's going to be mass by volume. We want a 20% by mass sodium chloride solution. So what would we do? Let's say we have 30 grams of sodium chloride. And we want to know how much solution is 20%. So we would solve that equation. 20 divided by 100 is 0.2, and then 0.2, well, 30 divided by 0.2 is 150. So you'd solve that, and it would become 150. So what you would do is you'd go to the lab, you'd put your 30 grams in a beaker or something, or in a flask, 30 grams of sodium chloride, and then you just add water while it was on the balance until it came up to 150 grams. Once it got up to 150 grams, you're done. You dissolve it, you've got your 20% solution. So when you want to make that kind of a solution, percent by mass is a good way to go. And sometimes in lab, you'll see, like when we have a dilute solution, it'll say 5% by mass or something like that. Usually, that's used for things that are not involved in chemical reactions, because that 20% by mass doesn't tell us anything about the moles. If we wanted to get this into moles, which we will do in our next lab, we would have to do a bunch of conversions and that kind of thing. So we can do it, but it's not really useful. So this would be used in a situation where you just need like some sodium chloride solution, and you don't care exactly how much it is for a chemical reaction. All right, so that's percent by mass. So skip the other ones that you'll see in the book, percent by volume and percent mass by volume. Not that those aren't useful concentrations or anything, but we're just not going to go through all of them because it's just too much to keep straight. So the next one, this one now, is more important. This is the most important one that we're going to look at, and this is called molarity. Molarity is the most important from a chemical standpoint because it deals with moles, which we know you have to have for chemical reactions. So molarity tells us the moles of solute per 1 liter of solution. And the unit itself is a big M. it is sometimes written like this, MOL divided by L, so mole per liter. And that's exactly how you calculate it. So if you remember that, that will help you calculate it. It is moles of solute divided by liters of solution. Molarity is a great tool for using a solution in a chemical reaction because, first of all, you know the moles. It's very easy to find the moles when you have a molarity measurement. And second of all, you measure it in liters or milliliters, which is a lot easier to do of a solution than dealing with the balance. So we use this a lot in chemical reactions, and I'll show you how to calculate it, and then I'll show you how to deal with it in a chemical reaction. So let's first just calculate a molarity, just a example molarity. Let's say we have, well, here, I'll just write out the whole question. What is the molarity of a solution where, I'll change colors here, 4.78 grams of sodium chloride solvent is dissolved in water. Hold on, sorry. Is dissolved in enough water to make a 25.00 milliliter solution. So we're going to calculate molarity given a certain amount of sodium chloride and given a certain volume of solution. Notice it didn't say 25 milliliters of water, it said enough water to make 25 milliliters of solution. Because most of these measures, the denominator is solution, not solvent. So the way you would do this in the lab is you'd use something called a volumetric flask, which is a special flask that has a really skinny long neck. We haven't used them yet, but we will. And it has just one line on it. And at that one line is exactly 25 milliliters. So you would put the sodium chloride in with a little bit of water, and then you would carefully add water until it got just to that line, and that would be exactly 25 milliliters of solution. So that's how you would make this. Now we need to figure out the concentration. So the formula for the concentration is given up here, moles of solute per liters of solution. But in this question, we're given grams of solute and milliliters of solution. So we have a couple conversions to do. Yeah, so first we have to go grams to moles. So let's do that. 4.78 grams sodium chloride. And we want to go grams of sodium chloride to moles of sodium chloride. To do that, we need the molar mass of sodium chloride. So we look up the periodic table, we add that up. I think it's 58.5. There's 58.5 grams in a mole of sodium chloride. Okay. So that's 0.0817 0.0817 moles. All right, so that'll be the top of the equation. So then the next part is the liters. We could probably do this by now. If you want, you can go through that calculation. But can anybody just tell me how many liters is 25 milliliters?
Zero.
Yeah, 0.025. So we can maybe just add this up here. 25 milliliters is 0.025 liters. We'll just keep those zeros in there because they're significant, but you wouldn't have to necessarily for our purposes. If you can't do that in your head, that's fine. You can set up another conversion and divide by 1,000. But now we have moles of sodium chloride and we have liters of solution, so we can calculate molarity. And let's just do it up here where we've already got it set up here. So that's going to be 0.0817 moles of sodium chloride divided by 0.02500 liters of solution. Which gives us 3.27, we'll say. And the way we would write this is 3.27 with a capital M, 3.27 molar. So a 3.27 molar solution of NaCl is a solution that has 0.0817 moles in 0.025 liters, or we could say it's a solution that has 3.27 moles in 1 liter. That's what that 3.27 number tells us. 3.27 moles in 1 liter, or per 1 liter of solution. All right, so let's look at it the other way. Let's try a problem where we know how much solution we want, we know the molarity we want, we have to calculate how to actually make the solution. Okay. Let's say we want 100 milliliters of a 0.153 molar NaCl solution. Which, by the way, is the standard solution that you'd get in like a saline solution in a IV bag or something like that. We'll talk about why that is in a little bit. We want 100 milliliters of a 0.153 molar NaCl solution. How much sodium chloride in grams do we need? So we need to figure out how much sodium chloride do we need to weigh out to actually then dilute to 100 milliliters and make this solution. So remember that molarity is moles per liter. So we can set up a proportion. If the molarity is 0.153, that's 0.153 moles per 1 liter. But we don't want 1 liter of it. We want 0.1 liter, right? 100 milliliters. So we can multiply it by 0.1 liter, cancel out the liters, and figure out how many moles would be in 1 liter. So that would be, or in 0.1 liter. So 0.0153 moles of sodium chloride in 0.1 liter, 100 milliliters. All right. So that tells us how much sodium chloride we need in moles. But we can't weigh out our sodium chloride in moles. We need to weigh it out in grams. So let's do that. Let's convert that moles to grams. So that means we're going to have our moles of NaCl on the bottom and grams of NaCl on the top. That's the same as before, 58.5. We'll do that calculation. 0.0153 times 58.5, 0.895. And that's our answer. So we would weigh out 0.895 grams of sodium chloride, dilute it to 100 milliliters, and we have exactly a 0.153 molar NaCl solution. Questions about that? So you can do a little practice with this and see how it goes. If we have time at the end today, we'll go back and practice some more of this. Otherwise, we can do that when we come back. I'll leave some space here so we can come back and do another example. But the last thing I want to talk about is something that we're going to do in lab in 3 weeks, 2 weeks, 2.5 weeks, I don't know. Almost 3 weeks after the exam, which is looking at suspensions and colloids and osmotic pressure. So far, there are three ways you can mix a solute with a solvent. There are 3 ways you can mix these kinds of things together. One we've been working on so far has been solutions, but there's 2 other ones too. There's suspensions and colloids. And these are mixtures where the particles are bigger than in solutions. Remember, solutions, they're broken down to the molecular level, and the solvent kind of goes in between the individual molecules or ions. In a suspension, you have still big particles of junk. In a colloid, you still have particles, but they're very small particles. So let me show a picture from the book here. It might make more sense than trying to describe everything. Somewhere. Yeah, here we go. Kind of a weird thing, but this is essentially what we're going to be doing in lab. So in this picture, you've got a mixture of stuff. The orange circles are particles that are in solution. The green triangles are colloids, and the red squares are suspension. So suspensions are the biggest particles. And the easiest way to tell a suspension is if you let the thing sit on the counter, those suspended particles will sink to the bottom. So anything that you have to shake is a suspension, because the particles are so big in a suspension that they're not really held by the solvent, they're just in there, so they fall to the bottom eventually. So have you ever had like medication that you have to shake up or something before you use it, or orange juice or whatever, things that you shake up before you use them as a suspension. A colloid is kind of like it. It's kind of in between the suspension and the solution, because it won't settle. and you can't filter it, but it's still not a solution. It's still in there. And so the way you can separate a colloid is by something called a semi-permeable membrane. A semi-permeable membrane is this kind of like a bag with very, very small holes that can only pass certain types of small molecules and can't pass larger molecules. Important types of semi-permeable membranes are things like cell membranes. So how do things get in and out of your cell? Well, through a semi-permeable membrane. That's why the actual structures in the cell don't move, just the stuff goes back and forth. So large proteins, things like that, can't get through the semi-permeable membrane. Starches, but small molecules that are dissolved in the solvent can get through that membrane. So in this picture, we've got the suspended particles settling to the bottom. We also see the suspended particles getting caught by a filter paper when it's filtered out. But neither of these do anything with the solution particles or the colloidal particles. The only way to change that is with the semi-permeable membrane. The larger suspension particles and the colloidal particles are stuck in the bag, but the solution particles come out and can go through that special bag. And we're going to make those special bags called the dialysis membrane in our next lab. So you'll be able to see that happening. Another way to spot a colloid is to look for something that's cloudy. If something looks cloudy, but it's not settling, that could be a colloid. So something like homogenized milk, like milk doesn't settle, the particles in the milk don't settle, but you can't see through the milk. Light won't make it through the milk very well. And so that's indication that there's colloidal particles, and that's all the proteins and starches and stuff that are in the milk, proteins primarily. Okay, so that leads us to the next thing, which is talking a little bit more about this semi-permeable membrane. When you set up a semi-permeable membrane, like in a cell, you introduce something called osmotic pressure. Have you heard the term osmosis? Anybody take some biology, know about that yet?
Going throughout the cell without water?
Yeah, osmosis is about water passing through a semi-permeable membrane, because water can pass through a membrane. So in your cell, for instance, if there's a difference in concentration between the inside of the cell and the outside of the cell, water will go in or out of the cell to try to correct that difference. And that can be a problem because that can damage the cells. So that creates a pressure. And it is actually a pressure, and it looks like this. Again, I'm going to use the book's picture so I don't have to draw it. In this case, we've got a semi-permeable membrane in between two waters, or two samples of water, one of which has sucrose dissolved in it. The problem with this setup is that well, not really a problem, but one thing that happens in this setup is the concentration wants to be equal. So water will move across the semi-permeable membrane to try to equal out the concentration, which means the water will move from an area of low concentration to an area of higher concentration of solute. So look what's happening here. Water is pushing through this membrane, and over time, it's actually going to go down from this side and go up in this side. So the water will actually move over to the other side in balance. And that's a pressure, because you could push something up with that. So that's why it's called osmotic pressure. There's a pressure against that membrane that is pushing the water, or pushing the level of the water up. And this is happening down at the molecular level. Individual molecules water molecules can fit through this membrane and are using that to push this up. So what happens is that can really change what's going on in something like your cells, depending on what the osmotic pressures are. So we're going to look at another picture here and look at some definitions. And then we'll go back and do some more calculations. All right, so here's a picture of what happens to blood cells in some different osmotic pressure situations. Now, to talk about that, we need to define these things. So we need to know what is an isotonic solution, what is a hypotonic solution, and what is a hypertonic solution. Has anybody heard these terms before? So you might already know. So what's an isotonic solution?
This is the same, the equal
Right.
concentration.
Iso usually means the same. So an isotonic solution is a solution that has the same osmotic pressure as the intracellular fluid, meaning this fluid inside the cell. Now, what gives rise to that same osmotic pressure? That means it has the same solute concentration. So the same amount of stuff is dissolved in the isotonic solution as in the inside of the cell. If we have that situation, then water is not forced one way or the other. It will go back and forth, but it basically stays the same. On balance, water isn't leaving or going into the cell. So most solutions that you want to put in your body are going to be isotonic solutions, so that it doesn't do anything to the cells. So like that 0.153 sodium chloride solution, or I believe it's a 0.3 molar glucose solution is another common one that we just talked about, that 0.153 molar, that's known as normal saline, because that's that isotonic solution. It's not going to mess with your cells. The other situations are the hypotonic and the hypertonic. And let's see if you can figure out which one is which based on what is actually happening in the blood cells. So if you put a blood cell in a hypotonic solution, it swells and bursts, and that's known as hemolysis. What's happening in that case then? Which direction is the water going? Is it going into the cell or out of the cell? Yeah, in this case, it's going into the cell. The water is forced into the cell, which makes it go, yeah, it gets bigger, and then eventually it pops. So in a hypotonic situation, what's the osmotic pressure? Is the osmotic pressure of the solution higher or lower? The pressure is higher. So what about the concentration? Is lower, right? So if you put cells in pure deionized water, that would be this situation. So a hypotonic solution has a lower solute concentration, and therefore a higher osmotic pressure. It's forcing the water into the cell, past the cell membrane, because of its lower solute concentration. And the trickiest thing about these is keeping all these higher and lower straight. So the lower concentration, the higher pressure, and watching on like an exam question what the question is. Does it say something about the osmotic pressure, or does it say something about the concentration? Because those are going to be opposite. All right, so then the other situation is the opposite, the hypertonic solution down here. The water is being pulled out of the cell, which causes it to shrivel up. So in a hypertonic solution, you have a higher solute concentration, and therefore a lower osmotic pressure, and that's going to force the liquid out of the cells and into the solution. There are some situations where this is something that you do on purpose, or that a doctor would do on purpose. Sometimes if you want to really quickly increase or decrease blood volume, you can use these techniques to pull water out of the cells or put water into the cells. And that can temporarily alleviate problems with like shock or swelling in certain areas or something like that. So, but that's pretty dangerous, obviously, because if you go too far, you could be really damaging the blood cells. So it talks a little bit about that in your book as well. All right, so that's the idea of osmotic pressure. It's also possible for solute molecules to go in and out of through these membranes as well. So it's not only the water that moves, it's the solute molecules as well. And that's something we're going to be testing in lab, and that's known as dialysis. So osmosis is when the water moves, dialysis is when the solutes move. And so that's, in lab, we're going to make a little baggie of glucose, starch, and sodium chloride solutions, and then we're going to watch and see what comes out of the dialysis membrane. Yeah, and it's probably could have been a lab you've already done in biology if you've done that before. All right, so let's head back up now. And with our last bit of time, we're going to practice some of these molarity calculations, because that's really an important part of what we're doing. So let's go to the book here and grab some practice type questions about this. Let's see if you can do some of these on your own. So the first one we'll look at is a basic calculating the molarity question, which is what we did first. So if you're given the amount of solute and the amount of solution, can you calculate the molarity? So give this one a try. See if you can calculate the molarity of an 8 gram of sodium hydroxide in 400 milliliters of solution. Keep working, but I'm going to start up here also. Did you get 0.5 molar?
Yeah, that's fine.
Great. That's it. All right, let's look at another type of molarity question. So you'll notice, watch the homework assignment carefully, because you'll notice a lot of these are calculating mass by volume solutions and that kind of stuff. We're not going to do that. That's not part of the course objective, so you can skip those. And actually, I should check. I can't remember if we're going to do dilutions or not. All right, well, you can take a look at this one. I'll look if we're doing dilution. So here are 3 different ones. They're all the same question, so if you just want to pick one and do them, or if you want to do all 3, that's fine. But this is the other way to ask that question, the more common way in a lab setting. If we want a certain amount of a certain concentration solution, how many grams of solute do we have to put in to get it? So that was like the second calculation example we did in the notes. You're going to figure out how many moles of the solute you need, and then convert that to grams. And take a look at that second example that we did in class. If you're not sure how to start, it's the exact same as that. Let me know.
We tandem back. We should tandem back on this.
Yeah, so this big mountain river is moles per liter. So you multiply this by the liters. That's the moles. This is
So let me start the first one here, just in case anybody else had the same question. Remember that this big M means moles per liter. So you're going to start there and go 0.450 moles per liter times the volume. That's going to cancel liters and give you moles. From there, you can convert to grams.
example, no, phosphorus, yeah?
Yeah.
30.9, but.
Call it 40, 31, yeah. Where was I? Oh, yeah. And we've only got a couple minutes left. I want to show you this other thing that can help you with this. Well, not on the exam because that would be cheating, and I want you to actually learn how to do this. But I don't know if you ever use this website, Wolfram Alpha. It's kind of like Google, like it's a search engine, but it does science and math stuff better. So we could say, I think, we'll try it and see, 0.428 liters of a 5 molar K2CO3 solution. Let's see if it figures that out. Usually it doesn't take this long. Maybe it's nope. So it didn't figure that out. But that was too much for it. But this thing can help you with some stuff like that. Like the second part here, 0.193 moles. Let's see if it gets that one. Oh, there it goes. Okay, I just had to write it a little bit different. So 0.428 liters of 0.45 molar K2CO3 means we need 26.6 grams. So do you see how I found that for us? So if you're doing a question like on the homework, but it doesn't have an answer, you could use something like this to calculate that. If you ever have a question, I use it also for like molar masses of really big stuff that you don't know. Like if you just type in K2CO3, you'll get some information about it, like that its molar mass is 138.2 or density, stuff like that. Whatever you want to know about it, the lethal dose of it. So anyway, that can be helpful while you're working through this stuff if you need, if you're calculating things for lab. Anytime where it's not really cheating, you just want to know the information. That can be helpful. All right, so that is it. I will be here tomorrow. Yeah, question?
I have a question. Did you round those off? Because I didn't round it off, so my answer was different.
What was your answer? Was it close?
266.19.
266?
Yeah, 0.19.
That's not really close. That's off by
It is.
times 10.
That's fine. Did you round those? Because I got 192.6.
Let me see. It looks like you're off by 10. Maybe
That's
it's
130.
wrong. Yeah. This times this should be 0.196, not 1. So you probably just left this in the wrong place.
All right.
Otherwise, yeah, it would be the same. I will be here tomorrow for office hours in the morning if anybody wants to come by. Otherwise, have a great break. And I'll see you in a week and a half.
It's okay. It's